Okay, good. Should I take it away?
Go ahead.
I'm gonna take this out. Okay, so hi everyone. It's wonderful to be here. I'm Dan Foreman-Mackey. I'm from Flatiron Institute in New York City, and I don't really know anything about RVs, but I know a lot of things about GPs, and I think about them a lot. And so I'm very excited to be here to learn some things, but also to share some of the things that I've learned recently. And so this is a tutorial. I didn't really know what that means, so it's going to be a little bit all over the place so that you know what to expect. Basically, I can't figure out how to take this. It's fine. What's going to happen is I'm going to start with some slides with some theory, and it's going to get like really heavy, and so I apologize in advance about that, but hopefully fun. And then I'm going to do some live coding on various different things. I'm very jet lagged, so this will certainly go well. And then there's going to be some like free form time to do various other things, and I'll have suggestions about that. Those other things could be going to the pub early if you so desire. I won't be offended. But anyways, so let's, oh yeah, I was gonna say, I did a test run of the live coding on the airplane, and I posted the results of that on this repository here. And there's a bunch of notes about how to get them running and stuff like that. And we'll come back to this in a few minutes, but one thing that I wanted to mention is that so there are a few different notebooks that have the solutions of hopefully what we're going to get to by the end. And you don't actually have to like install everything on your computer to get them to run. There's little links down here, and you can open them on Google Colab. And I have checked that as of this morning, they execute if you go through and press Shift Enter on these things. So anyways, so basically you should be able to play along if you want when we get to the sort of hands-on part, even without having like your full Python system set up and all that kind of stuff. Oh yeah, one other thing that's fun about Google Colab, if you're not used to it, is that it comes with free GPUs, that you have to enable them, but we'll talk a little bit about GPU stuff, and comes for free here. I would love this to be like interactive and stuff, so please shout at me and those kinds of things as we go. Good.
And if you're remote, please use the Slack discussion as before if you want to raise anything, and Baptiste will flag it if there's anything there. Yep.
Awesome. Yeah, and if people are heckling, feel free to mention that too. I can take it because I won't be seeing the Slack. That's too many things to navigate. Okay, so I'm going to start with these slides over here, and hopefully this doesn't go on too long. Okay, what did I want? Okay, good. Oh yeah, this is my contact info. And so if you're interested in any of these things, if you ever use my code, it doesn't work. You know, if you use my code and it does work, if you want to chat about any, you just get in touch any of these ways. It's fine. Okay, so the title of this tutorial is Scalable Gaussian Processes. And I think, you know, we've talked about a little introduction to Gaussian processes. I think probably lots of people here are very familiar with Gaussian processes. And one of the things that we've already heard today is that they can be computationally expensive, especially when you have large data sets. And so that's sort of the context that we're going to start with here is, you know, we want to fit a model that uses this log likelihood that you've already seen at least once today. I've written it in Python instead of in math, but that's because I don't know how to write LaTeX on this computer at the moment.
So you are going to give this tutorial assuming that everyone in this room understands everything about Gaussian processes.
That's a good question. I'm not going to give much of an introduction to Gaussian processes. I think I will mention some things that I think that there will be things that are useful, even if you're not super familiar with all the technical details and stuff like that. But this is going to be quite technical, and hopefully that's fun. Good. So this thing is the thing that we have to compute if we're doing MCMC or some sort of optimization. We want to compute this thing, maybe its derivatives, etc. And this involves various things. We have this residual vector, which is the size of our data set. We have this matrix K, which is the size of our data set by the size of our data set. And we need to solve this linear system right here. And we need to take the determinant of that matrix. And so as we all know, if we try to do this on a computer, something like this happens. And I'm going to talk about this plot a few times. So, yeah, question.
I just had a question about the previous slide.
Yeah, of course.
What are the @ signs denoting?
Oh, yeah, great. So this is a fairly new Python operator to indicate matrix multiplication.
Okay.
And actually, that's a great question because this is going to come up. I used the @ throughout this presentation to indicate that. So yes, great question. Matrix multiplication is what that is.
Thank you.
Good. Any other questions? Okay. So I did an experiment where I evaluated that function from the previous slide on this is a single core, some like decent machine. I don't know the details. Using a Python package called George, but in the background it's using sort of a highly optimized linear algebra implementation to evaluate the parts of that equation. You can see for small data sets, there's some Python overhead. We're going to come back to that a little later. But then as you get to larger data sets, things hit the expected n cubed scaling. And I think, I don't know, like I said, I don't really know anything about RVs. Maybe like 1,000 data points is not so bad. And, it only takes a second to evaluate that. So you might potentially be able to do some interesting things with that. But, I come from the world of like photometric time series where we're looking at hundreds of thousands of data points. If we tried to execute this, it would take a month to compute the likelihood once. This n cube scaling really sucks when you get to large data sizes. So this is the context. Okay, there's slightly more to a Gaussian process than just that one equation. There are these other two equations that you often have to compute. Again, I'm not going to go into too much detail here, but this is the predicted mean and covariance of conditioned on some data. What would you expect for future data sets? And in astronomy, a lot of the time we just use this for plotting, but there are various reasons why you might be interested in making sure that you can evaluate this thing decently fast too. And it has the same, you have to do this linear solve here again, and so that is, again, computationally expensive. So these are the things that we want to try to be able to evaluate for large data sets. Good. Okay, so I'm here because there's some things that we can do. We don't have to take a second for every model evaluation for our 1,000 data points. We don't have to take a month for our Kepler data sets or test data sets. And here are sort of the broad categories of solutions that I'm going to talk about today. And I included et cetera to accommodate all the other things. And I'm going to go through each of these in a little bit of detail. Okay, so first off, one solution that is awesome is just get a better computer or a bigger computer. You can use parallel algorithms. They're parallel linear algebra libraries. So if you have lots of CPUs and MPI support and all that kind of stuff, you can, you end up with this n cubed scaling for large data, but you can reduce the constant by a lot for like mid-level data sets. GPU acceleration, there's lots of excitement about that sort of from the context of machine learning. and lots of institutions now have access to big GPUs. And in fact, you can get some good speed ups from GPUs. I'm going to talk about that more later. And then I've incorporated iterative methods in here, which I didn't know exactly where to put it, but oh yeah, there was something I was supposed to say. I knew there was something I was supposed to say earlier. Okay, so one thing I was going to say is that the way that I think about this is as a linear algebra problem. So like, I see this and I see these matrix multiplications and these linear solves and these determinants. And I think we need a linear algebra solution to try to make this thing faster. And the et cetera includes other ways of thinking about it. But the way that I've always worked is trying to come at it from the perspective of improving your linear algebra support rather than directly thinking about Gaussian processes. So like trying to solve matrices faster rather than solve Gaussian processes faster. And so that may or may not be relevant, but it was something I wanted to mention. So iterative methods, for example, so this n cubed scaling, that's if you use some sort of matrix factorization to do your solve, and that gives you your determinant for free. But there are other methods like conjugate gradient or something like that, where you never actually factorize the matrix. All you have to do is take matrix vector products. And it turns out that you can, the asymptotic scaling of something like that would just be n squared, because that's the cost of applying a matrix to a vector. And it turns out that there are also ways of getting your determinant out of an iterative method. So sometimes you can get better scaling. And this is often combined with GPU acceleration, because GPUs are super fast at multiplying matrices, like way faster at multiplying matrices than factorizing a matrix. I knew that would.
You mentioned the determinant, and the determinant is absolutely necessary because it's part of the likelihood function. However, many people, sometimes you can separate the kind of kernel learning question from the extracting the process or fitting the process from the kernel learning. And then can you fully avoid taking determinants then?
I don't know that I understood all the words that you said. So one point is, if your kernel function is fixed, you don't have to compute the determinant. It only enters if you're trying to simultaneously fit or train the parameters of your model. And so you can get huge speedups from that. And so perhaps that's what you're talking about.
Yes, that's more or less. I was wondering if there's a regime in which you never need to get a determinant.
Yeah, I think, I don't know if you never need to get the determinant. If you know from first principles what the parameters of your kernel function need to be, then perhaps you could get away with that. But I'd say in all the applications that I'm imagining in this room, you're going to want to incorporate uncertainty on the parameters of your kernel at some level. So I think we're kind of stuck with it, and that actually, it's an interesting point, is that actually limits the kinds of linear algebra that we can use, because most people who work on applied math don't think about computing determinants. They just want to solve a linear system, and so that's where my idea of using linear algebra starts to break down. Any other questions? Good. Okay. Sometimes your data or your kernel function might have certain structure in it that you can take advantage of. So and we're going to talk a lot about this later, but some things, for example, we never have the luxury in astronomy, especially ground-based astronomy, to have uniformly sampled data. But if we did, then it turns out that you can get super fast linear algebra. Everything's beautiful, amazing. Life is great, but we never have that, which is too bad. So sometimes your data might live in a rectangular grid. Your data might be rectangular. For example, you have wavelength and time, where you have all of the wavelengths observed at every time. It turns out that the kernel matrix that you get out of that has something called Kronecker structure. There are ways that you can take advantage of that. I feel like there are tons of applications for that in astronomy that, as far as I know, haven't been hugely exploited. So I think it could be interesting to think more about. about things like that going forward. Sparsity, where here what I mean is that your length scale is small compared to the time baseline of your data set. Sometimes you can directly use sparse linear algebra methods. I've found in my work that doesn't tend to help very much. It doesn't let us scale up as big as we want, but it's something that is really interesting to think about as well. And then I'm going to talk a ton about quasi-separable matrices, because as my colleagues will know, I never shut up about this because I've been learning about them and lots of fun things. Okay, I'll come back to that later. Good. So structure is awesome. If you have structure, use it. A lot of the time you don't have structure that you can exploit. And so there are some approximate things that you can do, and outside of astronomy, this is sort of the state of the art for scalable Gaussian processes. So the simplest and like actually surprisingly effective method is just like use less of your data and then like try to correct for the fact that you're using less of your data. And there are like formal ways of doing that. And it turns out that when your computational cost is n squared, reducing the size of your data set gives you a huge benefit. So you win on the n squared part there. But it's just the result that you get is going to be approximate. There's sort of randomized linear algebra. I'm not going to talk too much about that, but you can do clever things with sort of randomly choosing rows and columns of your matrix to evaluate and come up with sort of bounded approximate values for all of the pieces that you need to evaluate your GP model. And then the last one is, and this is like the big thing in machine learning, is sort of using approximate structure. So for example, you might not have uniformly sampled data, but maybe you're close to uniformly sampled data, or perhaps you could make a very finely sampled, like a very fine grid that is uniformly sampled that crosses the domain of your observations. And it turns out that there are some really cool things that you can do to sort of interpolate onto this uniform grid, do all the fast stuff that you can do with uniformly sampled data, and then correct for the fact that you've interpolated. And I'll like mention ways that we might do that in practice in just a moment. Good. I'm throwing a million things. Okay, so then et cetera. There are all sorts of interesting things. I think probably lots of things that I don't know about. My corner of the literature that I know is restricted, but sort of within astronomy at least, there has been. We've discovered like stochastic ODEs and state space models and all sorts of fun things like that, karma models. And these are all ways of evaluating Gaussian processes in scalable ways. And there's a lot of overlap with the structured linear algebra methods, but it can sometimes be useful conceptually to think about your Gaussian process model using some of this terminology. But I'm not really going to talk about that today. Good. Okay, so I've thrown a million different ways at you. We're going to try to get a little bit more concrete. Oh yeah, what was I going to? Oh yeah, this plot. Remember that. So here are some examples of some of those things on this plot right here. So for example, the purple line labeled 1 here is using a better computer. So if you just like take your linear algebra, like your standard linear algebra library and run it on a machine with a GPU, then you can you get this purple line compared to the blue from before. And so you can see that once you get out to large data sets, the scaling ends up at n cubed again. But for moderately sized data, you get several orders of magnitude improvement in the runtime. And this will work for any kernel function, no matter what you want. If you have a GPU, you can get some nice benefits. And this isn't even using iterative methods or anything. This is just like using a Cholesky factorization on a GPU. Number 2 is celerite. I'll talk more about that later, and we've heard a little bit from Jean-Baptiste earlier about how this works. It has linear scaling, asymptotic scaling for large n, and it, so it makes a lot of things possible that wouldn't be possible otherwise. And then 3 is an example from, this is approximate linear algebra implemented in my package called George, but I'm not going to talk about that because it's probably just not a good idea to use it. Good. Okay, so now I want to talk a little bit about how to do these things in practice. We'll get a lot more details about this later, but it turns out that Gaussian processes are actually really straightforward, right? Like I actually already wrote the code, on the first slide, I wrote the code for how to compute a Gaussian process. Here's like a slightly more concrete version of that. This is how in Python you might evaluate the Gaussian process likelihood. This is the entire thing. I wrote it on the airplane. I didn't run it, but I'm pretty sure this is right. And so that's cool. So like you can just it's sort of easy to get started with this. There's some issues with this implementation. For example, I'm sort of doing double work by doing a solve and then computing the determinant separately. I can improve that. It only adds 1 line of code to improve that. Here's a version where we factorize the matrix once, solve the system, and we get the determinant for free. And this is actually like a pretty decent, like this implementation is more or less identical to the one that that I was plotting as our initial benchmark. This is like a pretty good implementation of the Gaussian process. And that's it. So why are there like 50 million different Python packages that implement Gaussian processes? The reason why is because evaluating that function is one thing, but there are lots of different things that you want to do with Gaussian processes. For example, you might want to like swap out different kernel functions or something, and like experiment with different things. You'd have to rewrite, because the kernel function was kind of hard coded in that version. We might want to, combine it with MCMC or some sort of nonlinear optimization. And specifically for this discussion, you might want to have some sort of scalable computations, which the previous implementation that I talked about doesn't permit. It's going to scale n cubed and have all of the issues that we were talking about. And so that's why many different packages exist for doing this. And myself, I have released 4 Gaussian process libraries over my young career so far. One might wonder why I would do such a thing, and I wonder that myself all the time. But then there are also lots of other packages. So you might even be familiar with, like scikit-learn has a nice implementation of Gaussian processes built into it. So this is something that exists all over the place. I want to specifically today talk about gPyTorch and TinyGP. Those are the ones I'm going to highlight. gPyTorch is I'll talk about it in a second. I didn't develop it. TinyGP, I did develop it. It's my like new baby, and so be nice to it. So gPyTorch is kind of the state of the art for these kinds of methods in machine learning, and I think there's a lot of potential to use gPyTorch in astronomy, and so I think it's something that's worth considering if you're trying out some. I think probably for a lot of the RV applications that we're going to talk about, there's enough knowledge in the community that gPyTorch isn't the right move, because it's really good if you're working with these like black box kinds of models where you want to be able to work with any kernel, with any dimensionality and those kinds of things. And I think a lot of the time we're not so much in that state, but there might be some places in your work where it's useful. And in particular, this is where the using iterative methods to get scalable GPUs is implemented. this is sort of like the baseline implementation of that, and it uses GPU acceleration and all of these other kinds of things. So there's lots of nice stuff here if you're like working in this black box state. Hog has a question. Does anyone else have a question first? Yeah.
I was going to say that in the machine learning context, Gaussian, this is a comment rather than a question, but in the machine learning context, usually often people are running the Gaussian process in a very big latent space. In this room, we tend to think of the Gaussian process as being a variable of time, like the state of the star is represented by a Gaussian process of time. But I think in the machine learning context, it's more like there's many features. You want to be able to make a nonlinear function of many features. And so sometimes it's hard for people in our community to read the machine learning communities writing about Gaussian processes because they're thinking about a function in a very high dimensional space where we tend to be thinking about a function in one dimension, or maybe if you do like intergalactic medium, 3 dimensions. But anyway, I just want to make that comment because it's one of the reasons why they're not so interested in our structured solutions.
Yeah, I think that's a good point. And I mean, the other point is just that even though the documentation is awesome for GPyTorch, it's not always the most accessible because we use pretty different language from this community. Yeah.
So I have a question. I'm starting to look at GPyTorch to fit data with millions of points.
Yeah.
And it seems that it is somewhat lacking in the approximate inference methods. I mean, they have KissGP and something like that, but not that much.
Yeah.
Do you know if there is a Python implementation of something with more support for approximate inference, or?
So what are you looking for in terms of approximate? Like, do you have specific methods in mind, or just you would be interested in experimenting with other methods that exist?
In experimenting with a little bit of methods. But.
Yeah, I must admit that I don't know too much. This is the best package that I know of when it comes to approximate inference, I haven't ever used GPyTorch, so I don't have like a huge amount of insight into it. I just know that like the benchmarks that I've seen are very impressive. And so I think it is worth exploring, but no, I don't know of like the best alternative if you're in that state. I know that this same group is working on a new library to do linear algebra using JAX, which we're going to talk about later. And perhaps that will include some interest. That's sort of where they're developing the new methods. But I think they're pretty focused on working on the methods that are developed within their group rather than implementing sort of a broader set of methods. But I'm not super sure. This is kind of the best I got. Any other questions? Great. Okay, so then the other one that I want to highlight is TinyGP. We're going to talk about it a lot more later. One thing that I wanted to show while we were here was this is that same scaling plot with different colors. And in particular, since I made that figure that I showed before, I've added this new green line here, which I'm excited about, which is using the Celerité algorithm, or like a generalization of the Celerité algorithm, implemented directly in JAX, as we're going to talk about later. Okay, good. Yeah, and so and this is where we start to get like really into the weeds, and I get really excited. Okay, so the idea behind that was so recently I discovered that there's a class of matrices called quasi-separable matrices, and it turns out that as Jean-Baptiste mentioned earlier, in Celerité, we said that the reason why Celerité was fast was because we were using semi-separable matrices. But then we discovered that the semi-separable matrices, in fact, weren't very numerically stable, and we needed to like use this preconditioner matrix in there, and we invented these algorithms to like work with these like preconditioned semi-separable matrices. Turns out those matrices have a name, and I just didn't know it. And there's a ton of literature about these matrices, but none of it is connected to Gaussian processes, as far as I can tell. one of the things that's neat is that these matrices are a broader class than just the semi-separable matrices. So it includes all the stuff that like karma models, but also the banded leaf noise models. There's sort of this like coherent story that like captures all of it, and so I'm really excited about that. And there are a few other pieces that I'm excited about that I'll talk about more in a second. But I think that this is going to be a nice formalism for thinking about these things, and this is what I've implemented inside of TinyGP, is this kind of linear algebra. Okay, so here's a quasi-separable matrix. This is the 4x4, and not necessarily symmetric quasi-separable matrix. And it looks a lot like a semi-separable matrix, except that we have these little matrices, these A matrices on our lower triangle here. And so I just wanted to I don't know, probably no one cares about this, but I wanted to show it anyway. So D is our diagonal, those are just scalars, each of those. So we have n of those. And then Q is like the V in the semi-separable case, and P is like the U, and so we have n of those, and each of them is a rank J. That's the rank of the system. Each of those is a vector with J1 elements, and then the A's are J by J matrices. And in the symmetric case, we could specify it just by the A, P, Q, and D. But it doesn't have to be symmetric, and sometimes it's useful to be able to work in the general case. And so it turns out that all of the things that I listed on the previous slide can be written like this. It has in the memory requirements are different. We actually have nj squared because we have these matrices, but it turns out that you actually don't take a huge hit from that, even in terms of like computational cost. The A's could be diagonal, and you could, and applying diagonal matrices is fine. But I've implemented the general case, and it's just as fast in my implementation as the not general case. Okay, too many details. Okay. Okay, so why should you care about this? And the reason why is because, like I mentioned, lots of GP models, and in particular, all of the things that we've been talking, or like all of the things like celerite and the S plus leaf and et cetera, all fit within this. So they're, this can help, thinking about these things can help, make all of the models that we care about fast. And that's because linear algebra for these types of matrices is fast. And it turns out that in the literature, sort of, people have derived all of the different algorithms that you need except for the Cholesky factorization. So the one that we came up with in the celerite paper is still useful. And so that's cool. But the thing that I was really excited about is that the group of quasi-separable matrices are closed under all of these operations. And that's nice because I think on the next slide, oh no, where is it? Yeah, here. So you can see that what we're doing here is we're, inverting, multiplying, adding, so it turns out that in fact, that means that sort of your predictive distribution is also a quasi-separable matrix. And so we get some nice benefits from that. And that was something that I've been trying to figure out for ages. And so I was really excited when I discovered these matrices. Just to give you an example of the kinds of algorithms. So here is an implementation for how you would compute the product between the matrix vector product. So if you have a quasi-separable matrix, this is the entire code for computing its dot product into a vector. So it's really straightforward, and it scales with n. It's 2n j squared. Yeah. And so you have these types of algorithms for all the things that you want to do, and they tend to be pretty straightforward to write down. So that's cool. Yeah.
I have a question.
Yeah.
What was the original motivation for quasi-separable matrix? Where did it emerge from?
Yeah, great question. I don't remember.
Okay.
Yeah. That's gonna, yeah, we should chat about, I can share some papers and we should chat about, the papers are pretty technical and sort of, they're more interested in like the applied math aspects, but they do list some applications that don't include Gaussian processes, but I don't even really remember what they are. Yeah. Yeah.
Does this only work? Does this only make sense for square matrices?
So that's a great
In
question.
the case of S, in
Yeah,
the
yeah.
original.
Yeah, so I swept that under the rug a little bit. I know how to compute I figured out that I haven't found any literature that talks about the general rectangular quasi-separable case. You can write it down. And I know how to take matrix products with it. I don't yet know how to do all the other things.
Okay.
But I think it should be possible.
Good. That's interesting.
Yeah. But I'm still working on that. Any other questions? Good. Okay, yeah, and then I implemented this in this TinyGP package. That's this green line right here. Compare that to Celerite. You can see for the large values, they're the same. But hilariously, TinyGP is a pure Python package. There's no compiled C code, which is fun. And so how the heck is it just as fast? And like I spent a huge amount of time on Celerite, like trying to like minutely optimize all of the C++ code and all this kind of stuff. And then I've just like written it in Python and it's faster. And in fact, like for small systems, it's way faster. And that's because of JAX, which is sort of the primary dependency of TinyGP. And I'm going to talk about that a little bit in a second. Good. I'm taking way too long. Good. Okay. Yeah. So now we're going to go to the live coding session. Were there any like questions online or comments online? No. Anything else in the room? Yeah.
Is there an intuitive way to understand why it's so much faster for low n and not for higher n?
Yeah. So I'll talk about it in more detail in just a moment. But basically, the way that so the way that JAX works is you write a Python function that looks just like NumPy code, and then you wrap it in a JIT decoration, which you might be familiar, like if you've used Numba or something like that. It's similar syntax, but completely different operating principles. But what it does is it like packages up your whole function into a single operation that gets performed either on your CPU and C++ or on your GPU and CUDA. So it can remove a lot of the Python overhead of communicating, because every time you call a NumPy function, it allocates new memory, and it has to go back between Python and C. And so for these small systems, and this blue line right here is the JAX version of the naive implementation, and so you can see that it also removes a lot of overhead in that case. But I'll talk some more about that in a minute. But it's pretty cool. Yeah.
I hope it's a quick question. I hope it's a quick answer.
Yeah.
So what are the requirements from the point of view of the kernels?
Yeah, great. Good. Yeah. So I don't really know sort of the full space of all the kernels. So like when we originally wrote Celerite, we thought it had to be 1D, or like that was the use case that we were thinking about, was 1D data. It doesn't necessarily have to be 1D. So like Jean-Baptiste talked about, it just needs to be sortable. So you need to be able to like put it in order. And so like, a time series with, different RV indicators, for example, is a nice example of something that would work. But then, there are other things that fit within this class of matrices that might be interesting to think about. And so I don't actually know, sort of the ones that are implemented in the code are sort of the things that we've been talking about today. And like Matern kernels you can implement those in this framework and stuff like that. And but I don't think we don't yet know the whole. So yeah, work to do.
But just to be clear,
Yeah.
you're saying that the kernels that people are currently using in Kepler and EPRB are in the class?
Yeah, I mean, so we can't exactly evaluate like the exponential sine squared kernel, for example, but we have some approximations that we can use, and I'll talk about some other things that we can do. But I think it spans the space of the kinds of kernels that we're interested in within this room, and probably more broadly. Yeah.
So is there a new kernel that you can do with quasi-separable representation that you cannot do with semi-separable?
Well, so I mean, one thing I would say is that we were never using semi-separable matrices. We were always using quasi-separable matrices. I just now have a name for it and some more literature. And in particular, you can write the more numerically stable Matern kernels in this framework in a way that's nicer. But we can chat some more about it afterwards. I don't think it's not like a fundamental change in the way that we're doing things, but I think it's sort of like a clearer picture of how everything fits together. But yeah, we should chat some more about that after. Good. Any other questions? Okay. So what we're going to do now is, let's see. So I'm going to do some live coding because that will be fun. For me. Oh yeah. So first I was going to show this first here. So this is the documentation page for TinyGP. This is we're not going to start with TinyGP, but this is sort of where we're going because I'm really excited about it. But in particular, I wanted to show that I've written tons of tutorials for this package, and in particular, they're things like we've seen a lot of equations like this today, and I talk through how to build these kinds of models, anyways. So there's lots of interesting things in here, including all of this quasi-separable stuff. So lots of things to check out in there, and even if you're not using TinyGP, there might be some relevant pieces in these tutorials. I've spent a lot of time on them, so I have to advertise them, I guess. Good. Okay, so I wanted to start with an introduction to JAX. People should feel free to go to the bathroom, I guess you have water already. If you want to leave, feel free. It's all a little informal here. But I wanted to start with an introduction to JAX because I think it's sort of the thing that makes TinyGP possible, but you also have to sort of think about how you code a tiny bit different in order to get all the benefits from it. And I think it could be useful just more generally in your work. And in particular, if you're using Python, it could be a handy way of speeding up or otherwise, adding some benefit to the things that you work on. Good. So the first thing that I do when I start a project in JAX is I do this. Can everyone see that on the screen?
Will you increase the font size a little
A
bit?
bit more, yeah? How about that?
Yeah, better.
Okay, good. So you have to manually tell it to use double precision. Don't worry about the warning. It's okay. There will be a few more of those. And the reason for this is that JAX it lives in the machine learning world. I should have said, so JAX is a Google product, which may or may not be a good thing. And it is built on top of TensorFlow, although you never have to know that you're interacting with TensorFlow. But in the machine learning world, people often use single precision math. And for most of the things that we want to do, that's not a good idea. So, so you have to manually turn it on at the beginning. So every notebook starts with that. I think there's an environment variable you can set too, but I like to be explicit about it. And then the primary interface that you're going to use is, and the tradition is to import jax.numpy as JNP, like that. And then JNP mostly works like NumPy. So, you can make a lin space, I don't know, like this. Another warning, it's okay. And we get this thing right here, which is like a NumPy array, but it has a different name. We don't need to worry about that too much. But let's just assign that to a variable. And you could do other things, like all your favorite, NumPy functions you can do, and everything kind of works the way that you'd expect it to. And so so JAX is kind of fun because you can use it just like you would use NumPy. Let's see, did I want to say anything else about that? Oh yeah, I mean, one other thing is, so oftentimes we'll, for reasons that may not be entirely clear right now, we'll often import NumPy as well. And so like if we had, some function or some variable y that's a NumPy array, we can combine them. So we could take the JAX sign of our NumPy array, and we end up with the same result. So you can like, it'll sort of feel like you can use them interchangeably, and then, but you can in some ways, but I'll show you places where you can't.
And if you add them, JAX will take over.
JAX will always win, yeah.
Can you do numpy.sign of JAX?
Yeah, that'll work too. And that's a good point. That's the place where NumPy wins. But there are places where we won't be able to do that, and we'll see it in just a minute. But yes, yeah. Any other questions? Good. Okay, so the first, okay, yeah. So one thing to remember, like the weird thing about JAX is that it wants you to work in a functional programming style, which is too much for our little discussion today. But basically, it's that you don't want to have mutable objects. So basically, what you want to do is you want to write. You don't want to like have classes with methods, which we've all been like ingrained to love in Python. Instead, you want functions that take concrete or like fixed inputs and return new outputs and don't change the values of the inputs that you get. So I can like write a function that takes in X, let's see. So you're going to find yourself writing like a bunch of little functions. I don't know. Say something like that. And this we can, call our function as usual. And we can also call that function with the NumPy input. Good, okay. Nothing too fancy there. But then the interesting thing is this JIT thing that I mentioned earlier. So what you want to do is you'll want to do jax.jit of func. And so what this is going to do is it takes a function as input and it returns a new function. And this function evaluates to the same thing. So we get the same answer. Doesn't look like we've won anything, right? But this is why we get that, why we reduce that Python overhead. And I'll show you sort of how this works. So I'm going to move it up here. So if you're not familiar with this decorator, with this decorator syntax, that's equivalent to like redefining function like this. So it passes the function through this JIT. operator. And so this is a very common programming style for JAX. Okay, so like I said, got that. Yeah.
Because this is why you have to code as with functions and not classes. Just to use the operator thing. Or?
No, it's a little bit more subtle than that. I'm not going to go into the details for why that is, but I'm happy to chat more afterwards. You don't strictly have to use a functional style. It's just very much designed in that mode. For example, you can apply jax.jit on a class method or something too. But okay, so so here's one fun thing, which is like slightly counterintuitive, is here, I'm going to put a print statement inside of my function, and then I'm going to evaluate it. Hello from inside, it says right here. And then if I evaluate it again, whoa, it gave me the same answer, but it never gave the print statement. And that's because it ran the function once to figure out sort of what happens inside the function, to trace the function, as they say, and then it knows how to evaluate this in the future. So you can rerun it many times, and there will never be any Python overhead because it's never actually executing the Python code. It's executing a bundled version of it that's just running on the CPU. A question?
If you want to preserve the print statement, is there a way to do that within JAX?
So I think they have some experimental feature to like print within JAX. It's not trivial. And so like, I like fully debug just with print statements. And so like sometimes it can be a bit of a nightmare. But the fun.
What if you put if true or something?
So yeah, that's a great question. We'll come back to that. So one thing you can do is you can just remove the JIT, and then it'll always run the Python if it's not JITted. So like that can be a way to like debug with the printing. But it's going to remove a lot of things like that. There's another question.
So the function must be run before first time, and then afterwards JAX takes over.
Yep.
So can you be limited by the large initial cost of the first evaluation?
Great question. So let's print X as well. So you'll note that X has no values when I run it. So in fact, when it executes, it doesn't actually ever take the sign of anything. It just remembers that it's going to need to take the sign of it. So there can be, like, if you had like a loop inside there that had, a million elements or something like that, then there would be some Python overhead. It's executing that, but for example, it's not going to be like passing around your full kernel matrix or something like that in Python when you execute it within a JIT.
Oh my God! I now have no idea what's going on. It executes the Python somehow once.
Yeah.
And then when it prints that device array, it's because it's returning something back out to the Python.
Yeah.
Jesus.
Yeah.
Okay, I don't understand any of the code I've written in the last.
Another question back there, yeah?
Also trying to wrap my head around it.
Yeah.
So if you run now the same function but on a different input.
Yeah, great
then
question.
You also do the.
Yeah. Good. Okay, so I ran it again with the same input, and it didn't print any of the things inside. Now, what if I like add 1 to that input? What do we think is going to happen?
No print.
That's right, no print. Now, what if I take all but the last element of X?
It's gonna be running.
So the things that are fixed, it has to know what the shape and the type of the inputs are. So that's the thing that it caches. So if you're reusing the same shape and type, then it'll reuse the. So like if we change it to an integer or a float or something, then it would run the prints again.
Yeah.
Question?
So if you then run it again, now all of them again, so the original code, is it overwritten it?
Oh, good question. No. So it uses so it uses a least recently used cache strategy. So it eventually will start throwing things away. I've never hit the limit. I don't know what sort of the technical details are of
If it
that.
said func X, it wouldn't print anything.
Yeah, that's right. Yeah, so it remembers those things. Yeah.
So basically what you define the first time you run it, it's like, I don't know, the space in the memory, and then it interprets how to use this memory space and how to do the computation to get the result.
That's right.
So then what you have to do if you change X or whatever, it just change the values, but then all the logic behind is like understood.
Yeah, that's right. And so that's why, so Hog asked a question, which was, let's keep our print in there. But so what if we do like, if, you know, like, something like that, right? Say something like that. What happens if we, so I'll remove the JIT for a second. So that works, right? But then if we put it back on, what happens? Oh, geez, it explodes. And that's because it doesn't know how to deal with the if statement. Now, what I could do is I could say, like, at x dot shape 0 is greater than 3, it's fine with that because the shape is fixed at the first time you execute it. But anyways, this is getting like way too insane. And we don't need to go into all of these details, but
So that means you can't JIT just anything. You can only JIT certain of your functions.
it depends. So basically, you want to try to, like, if you're using JAX, you want to try to JIT as much as you can. And so, but it turns out that, like, most of the time, we don't have conditionals like that. And, like, you know, if we're running a Gaussian process, like, we care about the shape, you know, when we first run it, but we're going to be using, like, you know, the same number of hyperparameters many, many times inside of our MCMC. And so, in fact, you get a lot of benefit for the types of operations that we want to do. Good. Okay. So the other thing I wanted to say was, let's get rid of some of these things here. So the other big thing that JAX gives you is, oh yeah, so one other thing I was going to say is, so right now it's running on my CPU. I don't have an NVIDIA GPU inside my laptop, and so I can't show you the GPU version. But what, oh yeah, one function that you'll get used to if you use JAX is func tools import partial. It's my favorite function. And it's something like backend equals GPU or something. And then, and if I run this, it'll crash. Yeah, because I don't have a GPU. But if I had one, then magically that function now runs on the GPU. And so that's sort of one of the things that's fun. Yeah?
This notebook, will you make it available? I know it may not make sense, but it's good notes maybe.
Yeah, absolutely. So there's a version on the GitHub page of this, which is like a much cleverer discussion with, like, I'd say, relevant words and stuff like that.
Okay.
So I posted a link on the Slack.
Yeah, I'm in there. That's fine.
Okay. I can also share this one if you think that would be useful.
It might be useful if you've heard what you said. So.
Okay, yeah, sure. I'll share this one at the end as well, and I'll try not to delete so much stuff. Yeah.
It should be a short one. Even when you're not using a GPU, it should be using like all the AVX fancy instructions and all that, right? So that's a huge push.
That's right. Yeah, and so you get some benefit from that. It's not actually. Let me think. I think if I do this, it'll work. Yeah, good. Yeah, but it's sort of NumPy, right? So like most NumPy installations will also use vectorized math for everything, and like multiprocessing and stuff like that. So in practice, you don't tend to get like, if you like just have like one huge matrix operation, you don't normally get a huge benefit from using JAX over NumPy. You get this benefit from the reduced Python overhead and GPU support in terms of performance.
So in some of these cases, for example, you will gain more from Numba than what you're getting from JAX?
So if you're, so far, numba should, I think, I don't really use numba, but I think so far, numba would be just as good for all of these things that we've been talking about. And in particular, if you have like lots of loops in your code, numba is like, JAX can't really handle loops. I'm not going to get into that, but we can talk about it more later. But the next thing that I'm going to talk about is the reason why is where JAX starts to win for the purposes that we care about. And that is because there's this other function, which is jax.grad of func. And so this is, we could also use this as a decorator. And so now we have a function to compute the derivative of our function. And so if we do something like this, we get the derivative of that function evaluated at that point. You'll note that I didn't do the grad func of x, and that's because the gradient is only, it's only meant to support scalar outputs. So they're imagining that most of the time we're going to be in this mode where we're computing the derivative of a log probability or something like that. And so you have a scalar output, and it can use that fact to get things fast. But there's one other function that exists that I'm not going to talk about at all, which is called vmap. And it takes a function that's defined on a scalar and maps it over a vector. And so what we can do, if we then do the grad func, and then x, that gives us the derivative of our function at all of our x's. And so that's fun. And so like the magic functions in JAX are JIT, grad, and vmap. And it's fun because you can actually put them in whatever order you want and stack them as many times as you want. And so we were talking earlier, like I think Jean-Baptiste showed like the equation for the derivative of the kernel. We don't ever have to compute that. We can use JAX to compute that thing and then still take the derivative of the derivative. You know, like we can stack all of these things on top of each other and get fast calculations of all of those kinds of things. Question here first.
To do this, do you need your original function to be only defined in terms of these JNP?
Great. Yeah, great. Yeah, what happens if I do that, right? It doesn't work. If I use straight NumPy instead of, so that's the place where you can't mix when you're inside of the function. And so you're absolutely right. It has to be just defined in terms of JAX NumPy. For these things work. Yeah.
We have an online question from Eric Ford. Does JAX use forward mode, reverse mode, or some clever combination of its autodifs?
Yeah, right. So that's a good question. JAX supports both modes and stacking forward and reverse. You can put them in whatever order you want. This grad function uses reverse mode. And sort of the interface we're working with forward mode is a little bit more awkward. But for example, if you want to compute the second, like the Hessian matrix or something like that, you often want to combine forward mode and reverse mode, and you can stack them however you want. And so, yeah, so those things are supported. Yeah, good question. Thanks, Eric. Yeah.
Can you use multiple arguments in test func?
Great, yeah, so we can. Grad by default differentiates with respect to the first argument. So it has this parameter argnums, which is which parameters you want to take the derivative with respect to. And so by default, it would only take the derivative with respect to the first argument, but you could make it take the derivative with respect to multiple arguments. But the next thing I'm going to show you is even it makes that sort of less exciting, which is like my favorite feature of JAX, and I wish NumPy had it every time I go back to using it. Okay, so the next thing is called pi trees, and okay, good. I'll show you what the deal is. Okay, so let's say instead of x, let's say we have like a params, and params is going to be a dictionary. Okay, so like let's say, you know, I don't know, like A and, you know, something like that, say. I don't know. And so then if we create some parameter dictionary with A and B, something like that, say, and then we call it. Okay, so good. Okay, whatever. We can evaluate that. It's not that exciting. But what if we do the grad of this and then call it with params? What that does is it returns the correctly structured derivatives. So we passed in a dictionary, and it's in the background figured out how to take the derivative with respect to all of the elements of the dictionary. And in fact, this could even be nested, so you could have entries in your dictionary that are themselves dictionaries. And for example, you know, these could be arrays, and it would broadcast appropriately over those things and all that kind of stuff. So like this, it seems like something small, but it's really pretty cool. And so we end up using this a lot in TinyGP, and so that's something that is worth knowing about. Good. Okay. So that, yeah. Question back there.
Just to see if I understood, if one of the thing inside params is an array, what happens?
Oh yeah. Good. Oh yeah. So so.
If you put a class inside, what does
so that's actually a good question, and there are times when you want to do that, and it's a little tricky what it does. So it has default behavior if you have NumPy arrays and tuples and dictionaries and like sort of the standard things, but if you have an arbitrary class, you have to like register it with the system, and there are other things you can do.
I was joking.
Could you overload the dictionary to do what you want?
Say again?
Could you inherit from a dictionary in your custom class and get the same thing?
Yeah, so exactly. So you do things like that, or the most common is actually a named tuple would be what you would use, since we don't want them to change. We want the values to be fixed. So if we did this, we can take I think we can, so this will work, right? But the grad doesn't work for the same reason that it didn't work before, because it only works for scalar outputs. But if we B-map it, then that doesn't work. Oh, that's because they both need to be the same shape. So that'll work, and it gives you back the derivatives in the right shape and all of that kind of stuff. Yeah.
I'm assuming you can, if you just know what values you want in your device array, you can explicitly define it. You have to do the lin space and.
Oh yeah, yeah. And so I normally create my arrays in NumPy. There are mechanisms for like So there are mechanisms for like manually assign, like moving it to the device and stuff like that. If that's what you were asking about, but
yeah, so like if you wanted, rather than like these like example,
yeah,
like I don't know,
real data,
yeah, way of doing that without having to figure.
Yeah, totally. So if you have a NumPy, like, so that could be a NumPy array. So if you have some NumPy array with your data in it, you can pass it in and that'll work. Yeah. Good. So we're not even at Gaussian processes yet. We have like a few more minutes. So I'm just going to save that and then do really, I won't go through, we may not have time to like show the full scope of everything that I wanted to do in this next section, but that's okay. We've had lots of fun conversations here. And the materials are available online to talk about some more, and I'll mention all that at the end. Okay, so here's now that we've got a little bit of a sense for JAX, I wanted to show a like slightly non-trivial but like pretty trivial Gaussian process case. So I've like simulated some data, it has periodicity, but the period is varying with time. So and I want to fit this with the Gaussian process. So I think I've already imported TinyGP, yeah. And so the first thing you would want to do is you want to define a kernel function. And so I even had some parameters I liked. If they're in kernels, we can have a return 3.2, say, and it has some length scale, and let's multiply it by a cosine kernel. So if you've used any of the standard Gaussian process packages, this will seem familiar. You take kernel objects, you add them together, you multiply them together, you multiply them by scalars, all of that kind of stuff. All of that works. And so now we have this new kernel object. And then we have a TinyGP Gaussian process object, which takes the kernel as the first parameter, and then you give it the x-axis, which I called x, and this diagonal elements. So what did I call that? Wire, but you actually have to square it. So what it wants is the thing that you add to the diagonal. And so there we go, we've got a GP, and then we can compute the log probability of that thing, and it's using JAX in the background to do all of those things. So all of this feels pretty familiar. One thing that's fun about TinyGP, which people may like or may hate, is so when you condition on data, so here I'm conditioning on the data and I'm giving it new x coordinates to predict at, we get this thing, and it has two elements. It has the log probability, so that's the same value as above. Oh, sorry.
Sorry, no, I was wondering, what does conditioning the data mean in this context?
Yeah, so this is, you want to predict future data or maybe make a plot for, I'll show the plot that everyone always wants to make in just a second.
Is it like training on data or?
So it's 4 fixed hyperparameters.
Yeah.
It's what would you predict as the the mean and variance of the data at new points. So it'll maybe be easier once I show the plot, and then we can come back to it if it doesn't fully answer the question.
It's what was called predict in your ancillarity, right?
So not quite.
Okay.
If you think about the GP is setting up a distribution over functions that share some covariance properties, and basically conditioning is like, I'm going to throw away all those that are not compatible with my data, and what's left behind is the conditioned GP.
That's right. And the big change with TinyGP, so there is a predict function that's the same as you have in George or Celerite, but in the background it does this. So there's a GP contained in the condition, which is the Gaussian process, like it's the full same Gaussian process object that you can do all the same things with, evaluated at the new points. And so this thing has this is the mean of the GP is called that. And so if we plot X grid in this, good, let me plot the data too. So here is a different order. Right there we have this is the conditional mean of the GP evaluated on a fine grid of points. And similarly, we can extract the where do I want to put it? We have a variance, which is the diagonal of that Gaussian process, which we often want to take the square root of. And so this is like this is the standard thing that you would do. And this is the plot that everyone loves. Between X grid mu minus mu plus. Something like that. And you get your beautiful prediction with the 1 sigma contours. And so this is sort of like a different way of thinking about this, and in particular you might not you might think that this would be a super slow way of doing this, but because of the way that jitting works and stuff like that, in fact, it's not ever evaluating the full covariance matrix for this GP unless you ask for it. Good. So what? Oh yeah. Okay, but this model's kind of garbage, so we want to optimize it. Okay, so let's do that, and then we're probably close to that. So the standard way, like this workflow that I'm about to show is like the standard way that we would do the like functional version of training a Gaussian process using tiny GP. And so we'd have a function that takes in the parameters of the model, and let's use this. So what we would do is we would have like something like this, and then we would have and you'll note that I'm using the log of the parameters here, and that's because we want them to always be positive. And something like this. Okay, so that's our kernel. It's the same as above, but now I've parameterized the different elements. And then our GP is going to be this thing, and it's going to take in the kernel, it's going to take in the x's, it's going to take in the diagonal, and then it's also going to take in a mean, okay, which we can also parameterize. Good, and so go for it. I'm going to keep typing.
Yeah.
I'm listening.
So is it going to be mad at you if you change X or Y error, even though, like, or I guess are you not going to JAX-JIT this build GP?
So the fun thing is that if you JAX-JIT that, it's going to freeze in the version of X at the runtime, I believe. Okay. Pretty sure. Okay. But yeah, no, it's not going to get mad at you. And there are some ways that JAX isn't really like functionally safe in sort of the way that you want. So you know, it may be better form to like pass in your X's and Y errors to that function. But you know, we're just hacking here. So what did I have? 0.3. Period. Let's just make that 0. And in fact, I can't just make it 0 for reasons that are slightly annoying, but just trust me. We want these to all be JAX objects here. Not for this cell, but for the cell that we're going to write in just a second. Good, so we could do build GP of the params, and that gives us a Gaussian process object. And then what you would do is you would define a loss function, so which takes in params, and it's going to return the minus build GP of params log probability of y. Good, and so then we do loss params. And there we go, we got a number, and for good form, we might want to JIT it. We don't actually have to in this case, but, and what's happened there is that when I run loss multiple times, it's gone through, this is why there's no Python overhead, is that it's no longer executing all of these lines right here. it just knows how to construct it knows all the logic to construct the kernel for a set of hyperparameters. And so all of that has been abstracted back into C++, which is cool. Good. So what else was I going to say? Oh yeah, we could do things like we can get the value and the gradient, and this is where the like pi tree stuff comes in. So we get the value of the function and the derivative with respect to all of the hyperparameters out as a dictionary, which is nice. And again, params could be some nested structure, and and so in fact, a lot of this was designed for like training neural networks where you have this like very complicated tree of parameter sets. Good, and then let's fit it. So I think I already imported JAX opt, which is another thing that wraps scipy.minimize and some other things. I think its parameter name is fun. Yeah. And it's going to be loss. And this is our optimizer, and we're going to run that with our params. We get and that ran, and that's the final negative log probability, and so it's better. So that's good. That was our goal. And then we can do things. We can do the same thing that we did above here. So we want to condition. So we're going to do params, and we're going to condition. We're going to get our standard deviation. Good. And then, sorry, I'm going a little wild over here, and there we go. There's our optimized version of the function right here. Looks better probably. Good. And so the last thing I wanted to say is yeah, we have like 1 minute. So the point of this discussion was scalable GPs. The scalable GPs live in here, and I was just going to demonstrate quickly. Do we have it jitted? Good. Okay. So we might want to benchmark a function in JAX. There's one other like wild thing that I didn't talk about, which is that it uses asynchronous dispatch. So that means that you have to be a little bit careful about benchmarking things because it tries to run as much as it can simultaneously if it can. And so you have to use this something like that, block until ready, I think. And then we can benchmark our it's using a lot of CPU up there. It's running away, and I think we have 1,000 data points here. I'm pretty sure. Yeah. There we go, and it took 20 milliseconds per evaluation for 1,000 data points. So it's not so bad. But what I was going to say, just to wrap things up, is so I could instead put in, which is this quasi-separable version of these things. And I think it'll be enough to just run this, and hopefully we get all the same answers. Looks similar. Good. Okay, we got a similar answer. I think it's actually identical answer. And then let's see if it's faster. Nice. 360 microseconds. And so that's sort of how easy it is to swap out and try different things. Of course, this is slightly artificial because I knew that this is one of the things I wanted to do. And so like the data has the right structure. The kernels that I chose also existed in both packages. Like there are various reasons why, this isn't the whole story, but that's pretty cool for, that's a pretty good speed up for, a data set of this size. Good. Question?
You mean the data is the right structure?
Just as in it's one-dimensional data, and so if you want to do things like these derivative models or variable amplitudes or multivariate types of things, there's a little bit more work to do. That's all discussed in this tutorial on the documentation page. Yep.
So you've calculated GPs, which you could previously do in other ways at a speed gain, but of course to me having to learn how to write code differently or something like that. Is this speed gain primarily for low numbers of data points here? In which case I would argue I can often already run my GP without waiting too long anyway. Or is it also for high N?
Well, I mean, the speed, I mean, if you're comparing to like celerity or something, for huge data sets, the speed is similar. But the thing that's nice about this is that so because we get all of the derivatives and that kind of stuff, in fact, your optimization and sampling and stuff like that will also be faster. If you're already using celerity 2 and IMC3, then maybe you don't get such a huge benefit from that, like specifically with this, but I think that there are going to be some places where it is worth it to switch over, just because the sort of infrastructure is developing better in the JAX world than in the piano world.
But the argument is we're already waiting a really long time, like we're already waiting days, even with celerity, because I'm trying to do some tests, NRV and something. There I won't get a real speed gain.
So yeah, you won't, like if you implement exactly the same model in both cases, and you have 100,000 data points or something like that, the like raw speed is not going to be better with this. That's right. Yeah.
A question from Eric.
Yeah.
You have a suggested reference for the underlying algorithm on the Quasi-Separable Matrix.
Yeah, great. So not yet. So I will say that I'm hoping to write some summary up of these things. I was going to say there is, so I have like buried like 17 pages deep in here. I've got some write-up of this with links to some of the key references and stuff like that. But no, they're like connection to GPs and the and sort of the all of the algorithms and stuff are not very clearly written down anywhere. But I'm happy to share this link in the chat after. Yeah.
A very practical question. If I understood correctly, looking at the documentation, this includes the kernels that are in George and the kernels that are in Celerite, right?
Good. Yeah. So yeah, we can look in here at what's implemented. There are a few other ones that don't exist in either. So I think here in the sort of baseline package, like if you're not using the scalable stuff, it's everything that's in George. But it's also much easier to write custom kernels. So there's an example in here for how you implement a new kernel, and it's much easier than it was in George, for example.
And if I have a big code that is choosing from one or the other, it's much cleaner.
Yeah, I think there are some interesting things. That sort of my main motivation for writing TinyGP was to improve the interface for building really expressive models. So that part of it should be better. And then for the scalable part, there are most of the same ones that are in Celerite, but we also have a few new ones. So the Materns and cosine and an explicit karma model. And again, it should be easier to implement custom versions as long as they fit inside of the in this structure. The other thing I would say is that there's also this like banded noise model, which also interfaces well with the scalable methods. Good, we should probably call it. It's been
Are there any burning last questions for Dan?
I have one more thing I want to say, actually.
Okay.
Sorry. while you think, if there's any burning questions. The thing I was going to say is, if you take a look at this on the GitHub page, I have some suggested things that I was hoping we would have time for you to try at the end of that, but I blathered on too much. But if you're interested in playing around with these things some more, this might be a good place to start. And it talks about how to do MCMC and adding some of the other kinds of things that you might want to do in your work. So this might be a useful place to start. And I'm happy to chat if you have any questions.
Okay. Well, that's fine, Dan. That was